Hi, everyone. Welcome to another episode of Oasis Bytes. As you may have seen in our previous videos, we are at home. Just like you, we are doing our best to stop the spread of COVID, and so we're quarantining ourselves. That means these episodes are coming from my beautiful kitchen, which is great. You know, I did the dishes, tried to clean it up. Anyway, today I'm joined by Warren. He's a software engineer at Oasis, and we're going to talk about confidentiality. So, as you heard in the previous videos, you learned about the separation of consensus and compute, these kind of two layers, the paratime layer and the consensus layer. And you learned kind of the services and functionality of each. Today, we're going to talk about a particular type of paratime, a confidential paratime. And Warren's going to talk us through how the network achieves confidentiality and really kind of why that's important for a blockchain network. So Warren, take it away.
All right. And we'll start talking about the idea of confidentiality itself. It's the property of a system not to reveal information to the wrong users. If you think about a very confidential system like a paper shredder, of course, if it destroys any data that you give it, then obviously it'll prevent the wrong users from accessing it. Now, we're not building a system exactly like that, though we always discuss confidentiality with the other side of this, availability. That's the property of a system to allow the right users to access their information.
Mm-hmm.
And other blockchains are very good at this. The policy in a lot of them is that any user can look at any part of the state of the system.
Mm-hmm.
But we're trying to build a system with both of these properties in mind. So some users can see certain data and other users can't see that data.
Interesting, but still in some ways be able to verify, you know, or have trust that the data is correct and that it's used correctly.
Mm-hmm.
Yeah.
Now in the Oasis network, we're using encryption to achieve confidentiality. Encryption scrambles data for a given key so that you wouldn't be able to unscramble it without that key. And that's nice because it's easier to move keys around than the data that you would encrypt.
Yeah. Yeah. Kind of. Sorry. Yeah. I was just thinking it's kind of like having a key to my house or something. Like,
right.
I obviously don't want to can't copy my house, but I can easily make copies of my key and give them around to friends or family or you, even if I wanted to let you come on over and get inside.
Right. The keys are small. And also, you can get a key once and then send multiple messages for that key later. So there's useful properties.
Yeah, really useful.
If the data is widely encrypted, then we can achieve confidentiality. I'm sorry, if the encrypted data is widely available, we can achieve confidentiality if the wrong users don't have that key. And we can achieve availability if the right users do have that key.
Got it. So we essentially need some system to help us figure out, you know, which side of this blue line are you on? Do you have access to should you have access to the data or should you not?
Right.
So how does the Oasis network do that? How does it figure out which users should have access and shouldn't?
Right. So then it's then going to come down to how we manage the keys in a way that matches this idea of who should and shouldn't have access.
Got it.
And so we're going to talk about that security goal, right? Let's break down the system into parts to think about that. Here's 3 of those parts: the end user, the executor node is one of the types of nodes on the network, and another type of node, the storage node. All right, and then we'll talk about an example of a program that you would run. Let's say a voting program where we can decide collectively where to have lunch.
And Warren, just to recap, in case folks forgot from previous videos, what is the executor node? Like, what does that do on the network?
So the executor node receives a batch of transactions from the transaction scheduler committee, and then runs that program code on some starting state, and then puts a batch of outputs and a end state. These outputs go then to like the merge committee, and then ultimately back out to storage, and as well as some information about this having taken place is sent out to the consensus layer.
Got it. So if you want to see kind of learn more about that, watch our previous videos on the paratime layer and the consensus layer, and they can walk you through kind of all the subtleties of it. But today we're talking about particularly that example program, right? This program where we're going to vote on where we're going to go for lunch later, which sounds great because I'm kind of hungry.
So in this voting app, uh, it takes, let's say, two things in. So one is like the previous set of all votes, and the other thing is this new vote that you're putting into it.
Yeah. Oh, sorry. There we go.
And then it's going to come out with two things. One is the new set of votes with this new vote added, and then in general you can also have a transaction output. In this case, let's say it's the current winning option.
Got it. So I voted for pizza, and I've now learned, unfortunately, that everyone voted for burritos, and so we're going to go get burritos for lunch.
Well, so the security goals for this about who's the right user for each 4 of these sort of arrows. On the Oasis network, let's start with the transaction output. That one's pretty easy. Like it's meant to go to that user.
Yeah.
And so what we can do is encrypt it for a key that belongs to the user. Now, these other 3 arrows, the transaction input and the state going in and out of storage, is a little weird because it's really only this voting program that should see it.
Yeah, like obviously you don't want the user to see it, but you also don't want the executor node to see it, right?
Right. So outside of the program, we don't want like the rest of the computer to see it. We don't want the owner of that computer to see it. And so that's something that a software system often doesn't normally have to defend against.
Yeah, I mean, because we're running on a blockchain network, right? We don't, inherently it's decentralized. We don't necessarily know who's running our node,
right?
Or who's running this executor node,
right? So on Oasis, the way we address this is we have a secure enclave on these executor nodes, and that allows. So a secure enclave has these 2 important properties that we use. One is isolation, which keeps the enclave separate from anything else going on that machine, separate from the machine owner looking at things. And second is remote attestation, which allows us to know what program is running in the enclave.
Got it.
So given that isolation in particular, what we can do is have a key inside the enclave specific to the program, and then have some of those other flows encrypted for that key. So the user can encrypt that vote for the enclave key, and the enclave can encrypt the state going out for its own key.
Got it.
When it retrieves it from storage, it will have been encrypted for that key.
Got it. So here we can see all the different keys. So this green key is the user's key. So they're receiving essentially the results back from the program, and they're encrypted inside the enclave and then decrypted by the user. And then here we're seeing the program's key, which again, any votes from the user or storage that gets pulled remains encrypted in transit, and then is only decrypted inside of that enclave. And that key, you're saying again, is specific to the program, right? So it's not like the system or admin or the node operator can go in and use that key to look at the data.
Right. It's just inside that enclave, and it's specific to this program, so that you can't access another program state either from within an enclave.
Got it.
So one thing to discuss is how this key gets into that enclave, right? The way this happens in this enclave-based design of confidential paratimes is that somewhere earlier on in the paratime's creation is that another kind of node called the key manager, shown here, will just generate a key from inside an enclave. Remember, the isolation keeps anything outside it from being able to see that key. And then that key manager's enclave is programmed to look at the remote attestation of another executor node, see that it's running the right program for this voting thing, and then deliver it a copy of this key if that indeed matches.
Got it.
Yeah.
And interesting. So in that way, we're able to correctly provision keys so that they can do this kind of song and dance of encryption and decryption later on.
Right.
Got it. Yeah, and we've learned about more broadly about the various services that the consensus layer and the paratime layer have. That have in previous videos. So feel free to go back and rewatch those if you're curious or want to learn more detail. We also have a bunch of docs, which I've linked below in the comments. So I encourage you to go read those as well, that have a lot of the nitty-gritty and kind of detailed technical information about how these different services work. And lastly, we do have an instance of a confidential runtime that we've developed at Oasis. It's called the Oasis ETH WASI runtime. And this uses a lot of the technology that Warren has described here today. Folks are welcome to go check out our GitHub repo. They can even copy the code and run their own instance of the Oasis ETH WASI runtime and connect it to the Oasis network if they'd like to. Links to that below as well. So take a look and let us know if you have any questions. We have a community Slack channel, which you can find on our website. We'd love to have you get involved. Anyway, thanks, Warren, for taking the time to chat with me about confidentiality. This was really interesting. Appreciate it.
Thanks.